Yeah, sure. Up to you.
Hello everyone, welcome to this week's string seminar. Today we are very happy to have Sridip, and he will tell us about universality in spin-refined high-energy data in higher D CFT. Please go ahead.
Thank you. Thank you for having me here. And it's always been wonderful to be at ICTS, to be in Bangalore. It's nice weather. So today, as Anurag said, today I'll be talking about universality in spin-refined high-energy data in higher dimensional CFT. And the idea is that in conformal field theory, the high energy data is generally universal. For example, there is a famous Cardy formula for density of states in two-dimensional CFT. But in higher dimension, we generally do not have modular invariance. But today, the goal of the talk is to convey the message that even without the modular invariance, you can say something about higher dimensional CFT, and you can prove some universal result about the high energy data in higher dimensional CFT. And specifically by high energy data, I will be focusing on high energy density of states. And the fact I say spin refined here, it basically means that I will be looking at high energy density of states and we'll be asking the following questions: is how this like asymptotic density of states gets distributed among various spin sectors. And as I said, that the main focus would be higher DCFT. But to set the stage, we will be starting with a two-dimensional CFT, and I will show you that how we can access this kind of spin-refined data in two-dimensional CFT using modular invariance, and from that point onwards, we will be asking similar question in the context of higher dimensional CFT, and we will be showing that similar universal results do hold in higher dimensional CFT.
Sridip?
Yes.
When you say high energy, since the CFT will not have any scale or anything, what do you mean by high energy then?
Oh, I mean D equals 3 or more.
High energy.
Oh, high energy is right. So by high energy, I mean so you are looking at density of states at large scaling dimension. So it's like delta. So all the operators are labeled by the
conformal dimension.
Yes, exactly. Yeah. So it's high.
I mean, but you'll probably say this, but I mean, in 2D CFT, we have different regimes where the scaling dimension scaling like the central charge.
Yes, exactly.
Will you let the central charge become big or not?
Yes. So in two dimension, we have all these different regime depending on how it scales with the central charge. And in two dimension, you also have the left movers and the right movers, and you can fix right movers and go take the left movers to left. But in this talk, mostly my focus would be like central charge fixed and delta going to infinity limit. Yeah. And presumably, so in 2D, like there is a usual Cardy limit, C finite and delta going to infinity, and then there is an extended regime. So in higher dimension, we would also expect there is some extended regime, but nothing has been told as explicitly as it is done it has been done in 2 dimension. So let me begin with two-dimensional CFT. So we have 2D CFT, and we consider unitary ones, And 2D CFT, the partition function also have modular invariance. So, and just by this fact they are unitary and they are modular invariant, we can prove a famous Cardi formula. Here's some echo, which is rho of delta in the delta going to infinity limit. So this is my density of states, or at some particular value delta, which is the conformal scaling dimension. And this is given by this universal formula, which is C over quarter exponential twice pi square root C delta over 3. The most important point about this formula is that this is universal. So it doesn't really depend on whether the CFT is free or is strongly interacting or not. If you give me this CFT data, which is the central charge, which comes with the Virasoro algebra, there is this universal formula for density of states. So this is universal, and the main point is it is controlled by a single parameter, which is central charge. Parameter, which is C, the central charge. And of course, like you may complain that rho of delta is really a distribution, because in a compact CFT the spectrum is discrete. So what does it mean to approximate a distribution with a continuous function? So a proper way to interpret this is really take this density of states and smear over a small window. But in this talk, I will bypass this subtlety about macrocanonical ensemble, and I will state all my results in the canonical ensemble, where you do not have to deal with this density of states or the fact that density of states is a distribution. So another way of phrasing this same universality is to say that you look at this quantity, trace e power minus beta h. So this is basically a thermal partition function, and you consider the beta going to 0 limit, and you can show that in the beta going to 0 limit, this thing is given by this universal expression. And in fact, this is how you derive this formula. Basically, you take this quantity and you do an inverse Laplace, and this inverse Laplace gives you this continuous function in the large delta limit. But if you phrase it in the canonical ensemble, then this is a very clean statement, and the statement is in the high temperature limit, the partition function is given by this universal formula, and again this is controlled by this number C, which is the central charge. And you can be a bit more specific, like you can also prove that if you consider this kind of quantity where you insert some angular momentum with I omega j, and if you take beta going to 0 limit, you can show that this thing will behave like exponential 4 pi square over beta 1 plus omega square C over 12. And again, the point is that it's controlled by the single parameter central charge. And to derive these results, you basically use the fact that your partition function is modular invariant, and in particular you use the S modular transformation, which tells you that Z of beta, which is this quantity, let me write it here, is same as Z of 4 pi square over beta. And the way you think about this is basically the Z of beta is a partition function on a torus. So there is a spatial cycle and there is a temporal cycle, but it's a Euclidean path integral, so you can exchange the space and time. And when you exchange this basically boils down to the statement that this Z of beta is same as Z of 4 pi square over beta. And then in the beta going to 0 limit, this quantity here goes to infinity. So everything gets projected onto the ground state, and the ground state energy is given by C minus C over 12. And this gives you this universal result. So that's how you derive the one version of the Cardi formula. But now you can ask, so at this point, this formula is not really spin sensitive, But at this point, you can ask two questions: that what happens to the other modular transformation? Because the statement about modular transformation is that there is a full group which is PSL2Z, and if you take any group element from this PSL2Z and act on the torus, the partition function will be same. So there is a whole lot of transformation which sits inside PSL2Z, and you want to ask what are the consequences of using these other transformations. And precisely when you ask about these spin-refined questions, they become useful. And so now I will introduce the quantity I will be looking at for most of the talk, which is trace e power minus beta h minus 1 to the power j.
For the second formula, don't you need to use some combination of, because you'll still try to get it back to the high temperature.
This one?
Yeah, you would not use the S transformation for that, right?
You use S transformation because you have to do it you have to introduce beta left and beta right. And beta left is beta times 1 plus I omega, and beta right is beta times 1 minus I omega. And then you do S transformation on both of them.
Each of them.
So you have 4 pi square over beta 1 plus I omega. And then another piece will be 4 pi square over beta 1 minus I omega. And then you add them up.
Right. But couldn't you also do it by considering a torus which is now with a non-trivial tau, and then you kind of...
So I guess the point is following, that here the non-trivial identification is beta omega, which is a slight twisting. So in the beta going to 0 limit, that twisting basically goes away. And that's why you are still allowed to do the S transformation and prove that the vacuum dominates. But the point you are raising will be very useful for this quantity here, because now it's not a small twisting. And this is precisely where, if you try to use the S transformation on this quantity, you will be failing to prove the ground state dominates in the S modular transformation. And that means you need to figure out what would be my appropriate PSL2Z transformation, which makes sure that after transformation, the ground state dominates. So before going there, let me just motivate this quantity. So this quantity weights the even spin and the odd spin with the plus sign and the minus sign. So in the microcanonical, even though I will not be doing the inverse Laplace explicitly, but you should keep in mind that in the microcanonical ensemble, this basically explores this following quantity, which is rho even delta minus rho odd delta. So some asymptotic behavior of the difference between these quantities. So the idea is that the Cardy formula gives you a approximate density of states, and in the leading order, they get evenly distributed between the even sector and the odd sector. And then there is some bump around this uniform distribution, and this bump is characterized by this quantity. And it will be so it will be a subleading information, but as I will be showing you that the modular transformation basically tells you that the subleading information is also fixed.
Sorry, it may be a very silly question, but this is not just a special case of that one, or is it because this?
No, it's not a special case
why
of
not?
that. Oh, because the point is, so here you're taking these quantities beta omega, you are taking beta to 0 limit.
Yeah, okay.
So
in that sense. So you just take omega beta fixed.
Yes,
now.
yes.
It is still sort of a limit of that, right?
No, because here this will blow, this thing has a pole at omega equals I, so
agree.
that means you cannot take omega going to infinity limit. So in other words...
No, I agree that this method doesn't work, but it's still a special, it's a different scaling simply from what you were doing.
Yeah,
before.
it's a
so you're using a different method because you're taking a different scaling on the same quantity.
Yes, because all I'm saying that this answer, if you...
This answer, of course, is no good because it's useless.
Yeah.
That transformation doesn't help you with that
Exactly.
scale, this
Yes,
scaling.
exactly.
Okay, got it. Thanks.
Right, exactly.
If you just do a S transformation, you will land in the Raman ground state, something like that?
No, this is the minus 1 to the power j, not minus 1 to the power f. So it's
If it was
even,
2j, then it would be...
But J and F are different.
so f is
is like
basically
2j.
e power twice pi ij, and this is e to the power pi ij.
As J is
J is all...
normalized as integers.
Yes, yes. So these are all bosonic. I am not talking about the
I see.
fermionic things
Okay,
at this point.
Okay.
So at the end of the talk, I will be mentioning about fermionics, and there's slightly more subtlety, and there, of course, this will happen.
I see.
Yeah. So these are all bosonic CFTs at
I
this
had a
point.
question. So why is even and odd special? I had the mind.
No, it's
Why can't you do some
you
mod
can
3
do
or
you
mod
can be
4?
more ambitious. You can do e power twice pi I p over qj.
Right, some phase, right, some rational.
Some phase, and you can do any rational angles. But I am focusing on -1 to the power j because that's the simplest one and it's easy to explain, so you get the idea. Okay. So now how do we determine this quantity? So to do this, we basically write in the usual way that this is trace e power twice pi I tau L0 C over 24 I tau bar L0 bar C over 24, and you can read up the tau, which will be I beta over twice pi plus half. Now the transformation you need to do is the following transformation, which is -1, 0, 2, -1. If you act it on tau, it will be minus tau, twice tau minus 1. And if you evaluate this quantity, you will see that this quantity is same as, after doing some algebra, 1/4 plus half. And again, if you take now beta going to 0 limit, this quantity goes to infinity. So again, everything gets projected to the ground state. So the upshot is that at the end of the day, you get in
rational number 2 because you are ending on a cusp.
Yes, exactly. So you can see this twice tau minus 1 is chosen in such a way so that it goes to the cusp. Yeah. So I cannot do this for any irrational number. And in the irrational, so irrational number, you have to approximate it by some rational number, and then you can do it. But then depending on how low your beta is, you have to might do a better approximation. So this behavior will hop.
But for rational number, it's
Yes, exactly. Right. So you take this exponential and let me color code it. This is 1/4 because this will become important. And then you have the piece 4 pi square over beta C over 12. And so the point I want to focus on here that we have a Cardy formula here. Suppose someone tells you the high energy growth of this partition function without insertion of -1 to the power j. So that means someone tells you this central charge. That immediately tells you that this quantity, what would be the subleading behavior or what would be the fluctuation over this uniform density. So it automatically dictated by this modular transformation, and you have this universal factor 1/4. So it's a concrete prediction. And if you do for P over Q, so let me write it down also for P over Q. So if you do trace e power minus beta h, e power twice pi P over Qj, so this is the most general thing you can do, plus I beta omega j. In the beta going to 0 limit, this behaves like exponential 1 over q square, and then the usual Cardy thing, C over 12. So again, the fact is there is a universal prefactor 1 over q square, which is related to this q, and the rest of the thing is same as the Cardy prediction. So a suggestive way to write this formula is the following. So I will be writing this relation in a suggestive way, and as you can probably guess that this result is what will be true in higher dimension as well. So the suggestive way is following: trace e power minus beta h I omega j e power twice pi I p over qj is in the beta going to 0 limit goes like 1 over q log trace e power q beta h minus I omega j. And if you just plug in this exponential here, you will see that this is true for 2D. Is the 2D picture clear to everyone? Okay, good. Let me keep it intact.
This is true from answer, but you're
Yeah, I have not, yes, exactly. I haven't yet.
true structurally.
Exactly. So now my idea would be to explain the hierarchy result and prove it's like, again, then you will see how it structurally appears. Yes, I haven't yet told you that, but this is something to keep in mind. So I am motivating it this way because we had the 2D result. It helped us to actually guess what we should be trying to prove in the higher dimension. Okay, so now there are two questions, as you can guess, that what about higher D? And I can make this question more precise. So what I will be I will be sketching the results for you, and then I will explain you. So first of all, I will show you that, yes.
Suppose you are trying to represent this as a partition function in ADS.
Yes.
Then this twisted partition function, does it have an interpretation as some kind of orbifold in R?
Yes, so for ADS3, if you do -1 to the power j, is you take the BTZ black hole with temperature twice beta, and then you do a particular Z2 quotient.
But Z2 quotient I would have thought will make it half of exponential half of what or the original. Right?
Yeah, but then there is a so first we start with 2 beta, and then you do the quotient. So that's half factor, and 2 beta is 4 pi square over beta. There is a 2 factor.
In general, you will start with 2 beta and then where is it?
Exactly. Yes. Yeah. In fact, like once I do the hierarchy in a more general way, like this prescription will become very clear that why I have to do this particular quotient I am telling you. And in ADS3 actually there is an easy way to also arrive at the same solution. You just do the same transformation, the modular transformation on the ADS thermal, and it will land up with the appropriate saddle. Okay, good. So the aim is the following, that I will first argue that this trace e power minus beta h in higher dimension also has a expansion. So this is an asymptotic expansion of this kind. So this is first what we'll argue, d plus 3 and so on. And then I will show you that if I insert like some quantity like this, schematically this will also have a high temperature expansion, and a priori this will come with some different coefficient, d plus 1, d plus 3, and so on. And so in 2D you can see that this series truncates here because there is only 1 over beta, and A0 is related to central charge. And in 2D basically the A0 prime and A0 is basically related by this 1 over q square factor. So the question is whether this unprimed, so we need to figure out the relation between unprimed and the primed ones, these coefficients in higher D. And we will also ask whether this is the end of the story, whether there are new features. So we will also ask whether there are new features. And indeed we will see that there are actually new features. So it's not completely determined. So there are some stuff which we need to specify. So these two will be our more concrete questions we will be asking. Okay. So now first I need to justify that there is a systematic expansion of this form in the beta going to 0 limit in higher dimension, because I do not have modular invariance. So the idea is to write down some effective field theory which systematically organizes this high temperature expansion. So how do we do this? We do the following. So we first realized that the trace e power minus beta h I omega j, this is nothing but a partition function on S1 times SD minus 1, where this SD minus 1 is slightly twisted as you go along the thermal cycle or as advanced by beta. So in other words, if you have some angle theta and tau, it is identified like this, tau plus beta. Now, the idea is that you are probing this path integral in the beta going to 0 limit. So in the beta going to 0 limit, the S1 cycle shrinks a lot. It almost becomes a point. So if the theory is gapped or under the KK reduction, if there is no zero mode, which you would expect generically in a strongly coupled theory, I should be able to write down some effective field theory which only depends on the background fields that lives on SD minus 1. So that's the basic idea. And to formalize this idea, instead of SD minus 1, we consider this following partition function, which is S1 times MD minus 1. And you assume this MD minus 1 is compact and it has a like rotational isometry, so it is meaningful to insert this kind of quantity. And you write down the metric in the following form, which is ds square is d tau as ai dxi. So this gauge field basically takes care of the fact that as you advance by the thermal direction, it gets rotated by some small amount. There is a dilaton, and then there is a metric on the base manifold, which is this MD minus 1. Yes.
D minus 1, you could have refined it by all the different angular momenta.
Yes, you can, yes.
But here that's why you're choosing sort of only one U1.
Oh, here just for presentational simplicity, I am just choosing one here.
But in MD minus 1, you're saying from the beginning there is only one. Is that what you're saying?
Oh no, so I'm saying, yes, so for this idea to go through, you at least need one thing. But in principle, you can have more stuff. Then you have to just keep track of those directions. Yeah.
Okay.
And yeah, so you have this thing. And then the idea is that this partition function should be same as Z gap, because I am assuming there is no zero mode, living on this base manifold. And then I can take beta going to 0 limit, and the physics idea is that this can be written down by a thermal effective action, which is only a function of Gij, which is the metric that lives on MD minus 1, the gauge field Ai, and the dilaton phi. Now I can also do a Weil transformation to absorb this phi into G. And we have to remember that we are dealing with a CFT. The CFT might have Weil anomaly. So by doing that, I can write it down as e power s thermal G hat Ij, where, let me write down the G hat. G hat is basically G times e power minus twice phi. And you have Ai, you have 0, plus there is some anomaly piece. And then the point is that this anomaly piece is there, and you have to choose some scheme and evaluate this anomaly on that particular thing.
So here you are saying that on MD minus 1 there is a various fields, one of which is the radius of the circle. That's what this phi is. Right?
Yes,
radius
this.
Basically, that's the beta.
Yes, that's related to beta. Yes.
But there will be other things like Wilson lines, etc.
Yes, but we have not included that in the partition function yet. So it's the most simplistic.
So the effective field theory will not, you don't need to do
the
effective field theory.
So the point is that so for example, you can ask the same question in the 2D case, and in the 2D case, there is a Wilson, if there is a Wilson line, that can only be sensitive to the ground state if the ground state has a spin, which basically means if you have CL not equals CR, and Cl minus Cr is 0 mod 24, then in the effective action you will write down a 0 plus 1 dimensional Chern-Simons term. And the level of the Chern-Simons term would be Cl minus Cr over 24.
Yes. So here you are saying that there will be such term in the effective action, but somehow they will not affect the final result.
Yes,
if you just try thinking of the effective action, then you also have to include those as massless fields, right?
Yes, so another way of saying thing that like, so if there are 0 modes, then you have to take care of the 0 modes. So I am basically at this point assuming there are no 0 modes and it's very clean.
Okay.
Yeah.
You said that it's expected that at high temperature there shouldn't be any 0 modes, but isn't it contrary to what you would expect?
No,
like
the
in quark-gluon plasma, something like that.
No, so the point is that quark-gluon plasma is not really CFT, but in this case,
something like n equal 4 super Youngmans or something.
Yeah, no. The point is for even in this case, the basic assumption is that suppose think of doing a KK reduction on this thing. The thermal mass gap would be scaled like 1 over beta. So unless there is a 0 mode under the KK reduction, so the statement about not having any 0 mode has nothing to do with high temperature or something. It's just the saying that the first excited state would go like, by just dimension analysis, would go like 1 over beta. And in the beta going to 0 limit, there is a gap. And you are assuming there, when you are doing the KK reduction, there is no n equals 0 mode, because 0 over beta can spoil the thing. But then if you have 0 mode, then it's not like everything will break down. It's not like that. You just have to take care of the 0 mode separately. And the contribution of the 0 mode is always subleading, and it will give you some log beta correction. For example, you can do it for the free scalar field. So so that's the basic idea.
Sort of a related question. I mean, you mentioned the anomaly also. There's in even an odd D, there will be some distinctions becoming with like some extra log beta terms or.
Yeah. So the point is that when you evaluate the effective action on SD minus 1, so this H is related to the dilatation plus some epsilon naught, some Casimir energy. And the statement is that you need to choose same scheme in which you evaluate the S anomaly and the epsilon naught. And but this equation is scheme independent. And once you do that, then you can do inverse Laplace and figure out the density of states and so on. Did I answer your question?
Yeah, no, I was just wondering about in even dimensions and odd dimensions.
Yeah, there will be, so in some cases there will be no anomaly.
No anomaly, yes. And here also in this there will be some log beta terms probably when you have D odd.
I see. I guess the statement is that, so if I write it down in a proper way in the e power minus beta D, then if there is no 0 mode, then there will not be any log beta piece. That's the statement.
I see.
Because they will drop out.
You're saying it will only come from the 0 modes.
Yes. The log beta pieces only come from the 0 modes. Yes. Yeah.
It's some measure term or something like that.
Yeah.
Essentially, it's a 1 over beta to some power.
Yeah, exactly. Yes. Right. Yeah, in fact, you can see it in the, like, if you just do free scalar field in dimension, then it gives you log terms, yes. So basically, to write down the effective action, all you need to do, you need to construct like while invariant and diff invariant term out of this G hat and this field AI. And once you do that, you will see that the partition function in the high temperature looks like following. This is exponential. There is some, maybe I should write down this way, it would be easier. So it's basically S thermal is integral dd minus 1x. Then there is a term square root G hat. Then there is a overall prefactor which is beta to the power d minus 1. And then you will have minus f, which is the cosmological constant piece, which is the first invariant term you can write down. Then there will be a term which is suppressed by beta square, which constructed out of the this G hat thing with the Ricci scalar. Then you can also have terms which constructed out of this AI, which is the F squared, the field strength, and so on. And sorry, I didn't write the coefficient, so this comes with C1, this comes with C2, some. So from the effective field theory point of view, these coefficients F, C1, C2, these are some data of the CFT. And the idea is that once you give me this data of the CFT, I can put the CFT on any manifold and I have to just evaluate this thing, effective action. So in particular, I can evaluate this R hat, F square, all these quantities for SD minus 1, and then I will get an expression for trace e power minus beta h for SD minus 1. And in fact, if I write down this expression, it will be like this, trace e power minus beta h I beta omega I j I, and then in the beta going to 0 limit, this will be exponential. There will be volume of SD minus 1, then there is a beta to the power d minus 1, there is a product of these fugacities, and then you will have F, the same F, and then you will have terms which goes like beta square. And now I need to look up my note because it's a complicated expression. So the expression would be d minus 2 times d minus 1 C1 plus 2 C1 8 over d C2 summation omega I square, and so on. So F is the same F. Oh, so the F is a Wilson coefficient. So you can interpret F as a thermal density, for example. It's related to the expectation value of T00. Yes, exactly. So in 2D CFT, F is twice pi C over 12. But in higher dimension, this is a new data, definitely. Like as far as we know at this point, it is a new data and is not related to any other central charge. And the same point is this. So the main upshot of this effective field theory that is basically separates out the dependence on the background and the CFT data, which is F, C1, C2.
I would have thought that the C1 should be get to the central charge. Maybe not. What in what dimension?
That is the 2-point function.
Yeah,
C1 is 2-point function.
C1 should be related to 2-point function because you are thinking I will be taking two derivatives. Yeah, but it's a thermal 2-point function probably related to.
Yeah, I think I was thinking in terms of 2 dimensions, but yes, this will be a 1-dimensional extension.
Yes, in 2 dimensions these terms are not there. It's just truncates here. Yeah.
So it's a 1-dimension. You are really over
Yeah. Yes, exactly. Yes. Yeah. In 2 dimensions it really truncates here, right? So that's why there is this term. Okay.
In higher dimension, the R hat would have been
Yeah.
related to the 2-point function. Is that correct? Like just like you said, F is related to the 1.
Yeah, I think it's a thermal 2-point function. Yes. Yeah, it's just taking just derivative and whatever comes out. And I think the F square piece would be related to probably charge fluctuations and so on. Yes.
What is capital F?
Oh, the gauge field because from the AI is F mu nu, F mu nu.
If you insert AI in the exponential, that's usually flat.
No, in higher dimension is so the point is if you write down the metric in this form, It's not flat. There is a F. Because of, okay, how do I say it? Like once you, like it's not flat, yeah.
Your gauge, but the gauge parameter is
No, because, so the point is you have to do this transformation and this yes. Mm-hmm.
so the gauge parameter will be just a function of
The gauge parameter will be the function of the circle.
So AI is basically the constant.
No, the expression of AI actually are much more complicated. It's not really exactly constant.
It depends on the ND minus 1.
Yeah, exactly. Yes.
I mean, in the background, probably AI will be constant. But you are not talking about the background. Like you are,
Let me.
But you're putting it on an arbitrary background, right? I mean,
Yes.
Relatively
Yeah.
arbitrary background. You choose the metric GIJ, you choose the dimension AI.
Actually, do I have the expression for AI?
So you are choosing to put it on
Just
isn't that what I mean? That's what I
after you write this, then you can say set them to background.
Yeah, exactly. Yes.
More general than just that twisted place that you.
Yes. So the point is here basically, yes, exactly. So it's more general in the fact that all I am assuming here that I am doing a partition function on this manifold with this AI. So you can make this AI as complicated as you. Yes. So all you need this in KK is, and then you are evaluating is on the SD minus. Yeah. Yes.
And the GIJ also is arbitrary.
Yes. GIJ is also, and then you are evaluating on SD minus 1. Yes. Yes, exactly. Yes. Yeah, I should also mention that. Yeah. So they are doing the hydrodynamic expansion, long wavelength expansion, and it's basically the same result at this point. Now, so this is all background, and now I want to ask that, like, I have this thermal effective action, and now whether I can derive this kind, or I can predict the behavior of this kind of quantities given this effective action. So the first point is that there is a pole here at omega equals I, which you can see basically from the fact that, like, physically it means that nothing can rotate faster than light, because it's like the sphere, the great circle on SD minus 1 is rotating with that omega. And this immediately tells you that you cannot use this effective action to describe, you cannot use that expression to describe this e power minus beta h minus 1 to the power j, which is same as saying that in 2D, if I take this expression here with beta omega and substitute the thing such that beta goes to 0, omega goes to infinity, I would not land up with this answer. So that means I cannot use that expression and recycle that expression to derive this quantity, and I have to invent some new trick. Is that clear? Okay, good. So let me go back to that side.
So just as a general, this thing in this expansion, you have a finite number of terms in any given dimension. There are only a finite number of these terms. And those, is it true that the finite number of terms that appear here with these unknown coefficients, C1, C2, they're all just related to some central charges of some kind, meaning appearing in 2, 3 point, some...
I guess the point is these are thermal correlators. So so there will be information from the excited states.
Oh yeah.
So I don't know directly how to relate them to the like A or C if you are imagining those things.
But I thought that the thermal state, but I thought you have taken out the beta dependence. So the beta dependence in the coefficients.
The coefficient doesn't depend on beta. That's true.
Right. So that's what. But I was thinking those C1, C2, those numbers. Those are specified by the central charges, the various coefficients in the...
I think it would not be that straightforward, like not directly related to. Because, so for example, if you can do that because F is the leading piece, so if you take the large volume limit, so in RD minus 1 times S1. Indeed, it's related to the stress energy tensor. But then other pieces are subleading. So I'm not entirely sure whether you can extract out in the large volume limit. Because naively, if you take this large volume limit, those things would be, in the beta going to 0 limit, those things would be 0 basically.
But
not dissipative transport groups, they were related to the fundamental anomaly. I mean, I remember that.
Okay.
I mean, one of the expansions were like non-dissipative transport coefficient, and they were related to this anomaly without. I mean, that is
So anomaly of what?
the chiral anomaly. I mean, in that.
Yeah, but those terms are not there in this picture because as I was saying that if CL is not equal CR, then there will be another piece which is CL minus CR over 24 times P inverse mod Q over 20 something. And now you can ask, how do I see that term from the effective action point of view? That would be some 0 plus 1 dimensional Chern-Simons term with a level K equals CL minus CR over 24.
So you're not looking for.
Yeah, no. So I am assuming that those terms are not there because for simplicity. Okay. Because I guess the main punchline, so this expansion. So yeah, so the point is that this expansion is important, but the main punchline is not this expansion. The main question is, given this expansion, can I predict something about that grand canonical ensemble? And the first thing, naively you might think that I just substitute beta omega with whatever value there is, but that doesn't do the job. But coming back to Rajesh's question, I think it will be very nice if one can concretely show that these coefficients are related to some central charge or something, because then there will be monotonicity property and you will have some bounds on this thing. But as far as we know right now, there is no such bound, except for the fact that F is positive or non-negative. Okay. Now I want to do like probe this quantity. So to probe this quantity, I will go back to the 2D one, and I would like to derive this 2D result, but using the language of thermal effective field theory so that I can easily generalize that technique to higher dimension. So let's again go back to our simple example, which is trace e power minus beta h minus 1 to the power j. So what is this quantity? This quantity is the following, where basically you take a torus and let me divide into two pieces. So this is L over 2, this is L over 2. And because of this minus 1 to the power j insertion, as you advance by beta, you basically rotate your S1 by pi. So which basically means that this part is identified with this part, and this segment is identified with this segment in the path integral. So I am doing a path integral over a manifold with this kind of identification. So now what you do, you basically realize that this piece and this piece are identified, and I am doing a local field theory. So I can cut this piece here and stack it on top of it. So that's a simple manipulation you do. So let's do that. So I will, okay. This thing is, let me write it here. Sorry. So if you do that, you will have this dotted line, and here you have this thing, you have this thing, and this thing is identified with this, and now this length is twice beta. Now you have some weird identification because this thing is identified with this, and of course this thing is identified with this. But the point is, in the beta going to 0 limit, this is almost like in the cylinder form. And in the beta going to 0 limit, this weird identification doesn't matter. So it's as if you are doing an effective field theory. So you are doing a thermal EFT on a different manifold which has length twice beta, and this part is L over 2. And recall, in the usual Cardi, we know that the usual Cardi formula works like exponential for, let me write it again in a suggestive form, which is twice pi. This is the volume of the S1. There is beta, and I told you that F is basically this. But now what you do, if you apply the thermal EFT on this twice beta, your beta becomes twice beta. This L over 2 produces a factor of half. And that precisely the factor of 1/4 that appears here. And this argument is very general. You can, instead of -1 to the power j, you can insert e power twice pi I p over q, and then you have to basically cut it into q pieces and basically take them and stack them on top of each other. And once you stack them, you will basically, this length will become q beta, and then there will be a prefactor which is L over q, which is 1 over q. And this resonates well with this formula I wrote down here. So you have beta to q beta, and then there is a prefactor which is 1 over q. And this L over 2. Yeah. So in general, you will have a 1 over q here. So 1 over q here, and this will become twice pi over q beta, and then this is twice pi c over 12. And now look, this argument doesn't really care about the fact you are on S1. You can play the same game on SD minus 1 times S1. You have to, for example, you have to cut the sphere into pieces and then stack them on top of each other. And this immediately tells you that in higher dimension, the leading term will behave like, so the leading term go in higher dimension, so in higher D, the leading term goes like F times volume SD minus 1 times beta to the power D minus 1. So now,
Sridip,
yes.
I just had a question about the previous thing, the torus. So you had a P over Q earlier.
Yes,
But
yes.
the P dependence is not visible in this leading order because
Yes.
once you stack these things
Yes.
on top of each other, you don't really care how they're identified.
Yes, yes.
You just
yes.
replace it by just this
Yes,
uniform.
yes, yes.
That's why you don't see a P there.
Yes, exactly. But you can see the, I'll come back, but there is a subtlety and I will come back to that. So for example, in 2D, if you have CL minus CR is not equal 0, you can see the P dependence.
And even in that matrix, right, if you do it for P by Q, that matrix will be something like P prime, P, Q, and something else.
Yeah, the matrix will be, I can write it down. This will be Q minus P. This is minus P inverse mod Q, and this is some S so that it becomes
The
one.
Euclid's division thing.
Yes, yes, exactly.
Yeah. So then if you apply that on tau,
Yeah.
the shift that you get, the half will be replaced by that P inverse over Q.
Yes, P inverse over, yes, exactly,
But
yes.
that will
Yeah,
go
and
with
that's, and
L0 minus L0 bar.
yeah, so you will have some here P inverse something, P inverse mod Q.
Yeah.
And then if CL minus CR is not 0, not if CL minus CR is
Right,
not 0,
yeah.
then that will be sensitive to that piece.
To that, right.
And it is same as saying that basically there is a non-trivial identification, so there is a non-trivial holonomy of the gauge field, and only non-zero spin stuff can be sensitive to that non-trivial holonomy.
Thanks.
Clear? Good. So as I was saying, in hierarchy, the leading term goes like this, as you can see from that expression. So if I do this transformation, I will have a factor of q to the power d minus 1 from this beta, and then volume gets a 1 over q. So a concrete prediction is that if I insert this e power twice pi over q, then f goes to f over q to the power d in higher dimension. So here I have 1 over q square, and in higher dimension this 2 just becomes d. So in higher dimension also the subleading information is completely controlled by the leading information. So once you know the F, you know also the subleading information and how the density has a bump over the uniform, how the rho even and the rho odd has a bump. Okay. Now let me be slightly more concrete, and because I explained.
If instead of SD minus 1, you had some torus kind of thing,
Yes.
then you could use the same modular transformation, right? You could exchange the
yes,
S1s.
exactly. So yes.
And then you'll get a similar result there?
Yeah, the prediction is same. So one more point is that here, the only thing you need that there is some isometry, and it doesn't need to be SD minus 1. So you can also do it for the torus, and there will be prediction. Yes, there will be massless modes, but I suspect the massless modes will always contribute in the log beta piece. So you can probably separate them out from the leading behavior. Yeah, that's true. In torus, there can be massless modes. And in torus, you can play other games that Edgar played some time back, almost 7 years back. Like you can swap the cycles and do the modular transformation. And I suspect for the torus case, even so, this expansion is basically asymptotic expansion. For the torus case, I would imagine it would be a convergent expansion because you have some Hilbert space interpretation in the dual channel.
Yeah.
But shouldn't it be universal? I mean, the high energy density of states should be universal, no? I mean, it shouldn't depend on MD minus 1.
No, why do you say so? Because so the point is that the number of operators is universal because it's a conformal field theory. But state operator correspondence only works with SD minus 1. So of course in leading order it will only depend on the volume, for example. So the leading order is always F. But then if you put it on a torus, the next term will be, I think, it can see the difference, for example, the next term.
So, so you're saying, no, it's true that state operator correspondence works. But for something with maybe a torus is special because it has this massless mode, but something like, I mean, a squashed sphere or something and they will all presumably have similar.
Yeah, so these are all subleading effects. So you can imagine like this, that suppose you are counting the number of eigenvalues of Laplacian on a manifold. There is a leading growth, which almost like the flat space, but then the subleading terms actually depends on how they are carved, whether there is boundary and not.
So those terms, C1, C2. And
yeah, those terms will see that. In fact, speaking of that, you can probably generalize this idea even with a thing with a boundary, and then you have to consider contribution from the boundary terms and so on. Like there will be another effective field theory lives on the boundary.
But that's where, again, I was thinking, if the C1 and C2 are fixed by some central charges, then those are universal.
That's true, yes.
Yeah. So I mean, yeah, definitely the subleading, I mean, these pole terms that you have, which are blowing up as beta goes to 0, you might have expected some universality, but you have concrete examples where, for different, I don't know, if you do SD minus 1 versus say SD minus 1 by 2 times SD minus 1 by 2 or something like that. I mean, like you break it up, let's say S4 into S2 times S2 or something like that. Will S2 times S2 be different from S4? I mean,
well, I haven't checked it, but I would, like this will predict that they will be different. And in the subleading order, yes.
Subleading means not in the dots, but in the like beta square term itself.
Yes, exactly. The R-hat will be different, right?
But the coefficient, so that's what I was wondering. The coefficients C1 and C2 are all that.
Yes, exactly.
Those are universal or not is the question.
Oh no, so the point, universal in the sense that if you take a CFT, it's fixed once for all.
Okay.
But I am saying that at this point I do not know whether you can relate it C1, C2, some central charge that we know of. But the whole point of this expansion is to separate out these two datas. That one data that comes from the CFT, once you know the CFT, AF, C1, C2, everything gets fixed, and then you can put it on any manifold and just evaluate it. And then the claim is that if you know this expansion, then you know basically this AF, C1, C2, all these coefficients, and then you also have a prediction for this quantity because of this relation, which is a priori not obvious that it should hold. So in 2D it comes from modular invariance, and well, like looking back, you can say in 2D it comes from because of this path integral manipulation. You do not need the full-fledged power of the modular invariance.
So here up to order beta square, if you knew the result for 3 different manifolds, then you have everything. Is that
Yes,
right?
yes, exactly, yes.
Okay.
You can separate out them, yes. Yeah, that's also true. Yeah, you can try to do different. No, fix the manifold and
Just S3 or SD minus 1.
yeah.
We say you put on all the custom vary the.
Yeah. For example, you can compute the free scalar. You can put the free scalar field on this manifold and do the plasticity exponential because you know the operator counting, and you can read up all these coefficients. And another thing would be you can take the, like, for example, in ADS3 you can take the appropriate solution, BTC solution, and you can compute the entropy and read up the things. And you can also do it in a higher dimension, like in ADS car and so on. Okay, now there are some subtleties here that I want to emphasize, but before that I need to put some equations on this stacking picture. Like this stacking picture is very nice, I like it, but we want to be a bit more precise. So here I told you that I am doing a partition function on z of s1 times sd minus 1. Now I want to say that I am doing a path integral over some manifold. So what is this manifold that I am doing a path integral over? And the claim is that I am doing a path integral over the following manifold, which is z s1 q beta times sd minus 1 slash zq. And where this action of the zq is the following. So zq basically acts on the unit vector. So you take a unit vector from sd minus 1, you take tau, and it rotates the unit vector such that r to the power q is 1, and it advances tau by tau plus beta. So this is the path integral description of trace e power minus beta h to twice pi I, this quantity basically, where with omega equals 0. If omega is non-zero, then you slightly have to twist it, but let's just focus on omega equals 0 thing for now. And then the idea is that the idea of the effective field theory is, so this is a, like if you take beta going to 0 limit, you can interpret this manifold or treat this manifold as approximately equal to s1 q beta times sd minus 1 slash zq. So this is not entirely true because this is a non-trivial manifold. But then you can approximate it by this, and this will also explain the fact that why there is a q beta sitting here because of this s1 q beta, and this quotient basically gives you this 1 over q factor. But now as we know that this manifold and these manifolds are not same, so what you can do, you can like place a coordinate system where locally these two things look same, but then the fact that you have to remember there is a non-trivial identification which you can introduce by introducing a gauge field. And this gauge field will have a non-trivial holonomy which keeps track of this non-trivial identification. And this gauge field will also be sensitive to the fact that whether there is a P or not. And again, it goes back to the discussion when CL minus CR is not 0, and we will see these terms. So the upshot is that in some cases we can have some topological terms. SD minus 1 mod ZQ, yes. Yeah. Yes, exactly. Now then comes the next point. Yes, right. So for 2 dimension, we were very lucky because S1 is we rotate by pi and there is no fixed point. But if you do it on S2 times S1, immediately you will end up with a problem because S2 times ZQ always has a fixed point at the north pole and the south pole. And okay, I deleted the piece here. There somewhere I wrote that whether there are new features. And this is exactly the new features that do not appear in 2D, but they are there in higher dimension. So in any odd dimension, like suppose you do S2 times S1 or S4 times S1, you will always, whatever you turn on, because the number of cartons are short, so like there are not many cartons, not enough cartons, so you will always have a fixed point. And even in even dimension, like if you do S4, you might, like there are multiple carton direction and you can create a scenario where there are fixed locus. And then we have to take care of this fixed locus. And then the proposal is the following, that we should be writing down an effective field theory which has support on this fixed locus. So I will have another term here which is S defect. So these are like some defects which lives on the SD minus 1. And one important thing is that this S defect is always higher codimensional objects. So these terms will never compete with this leading piece I write down here, this F term. But in principle, it can compete with all these pieces like R hat or C2 and so on. So if we care about these pieces, and if there are fixed points, we should also be figuring out this piece because they are important. And again, you can take a free scalar field on S2 times S1. You can do a plastic exponential because you can count the operators. And then you can identify all these pieces. There will be some pieces which follows this rule, and then there will be pieces which is S defect.
D minus 3-dimensional manifold, and
Yes.
so wouldn't that also have a similar expansion?
Yes, exactly. So I haven't, like we have written down, so the simplest case you can do is S2 times S1 where there are points. And then you can realize that the terms you can write down is a constant. And you can evaluate the R hat on that north pole and the south pole. You can have terms like Hodge dual of F. And basically these are, and then derivatives acting on that. And then basically you can construct all the terms with this. In fact, I can write down the expression for you, which is, where did the button go?
You just evaluate various scalars at that point.
Yes, exactly. Yes. Scalars which are ZQ invariant. So the rule would be that because the manifold has, so you write down all possible diffeomorphic invariant terms on this manifold which are ZQ invariant around that. And if you have multiple fixed locus, then you have to be a bit more careful that you have to lift it properly and you have to write down the terms which are invariant under the subgroup which fix that locus. So in higher dimension things will become more and more complicated, but the process is same, that you just look at this expansion and look at this expression and just write down all the invariant terms. So let me write down the one for the S2 times S1. I can erase this. So this will be this. So there will be a piece which goes like this, a contribution from the north pole and the south pole, so the constant piece. And then there will be piece which goes like beta omega. So these data is A0 and A1, these are completely new data, as I was mentioning, that they comes with the defect. And then there will be piece like q beta square over q 2 plus tan omega square. Then there is minus p over q plus 4 omega square p over q plus, and so on. Now I want to point out to one nice thing that happens. So earlier I told you that there is a reason why there is omega equals I pole, because the great circle cannot rotate more than like faster than light. But now when you do S2 times S1, these are points. So that means you should not expect any pole in omega, and that's what happens. Like there is no pole in omega in the defect action, and it's all polynomial. And if you go to in higher dimension, like more than d equals 3, then basically you can have various fixed locus, and depending on which omega, like there will be restriction on some of the omegas, that some of the omegas cannot go faster than 1. So you will have, so there will not be any symmetric scenario. There will be some poles in omega 1 and omega 2. In some terms there will be pole in omega 3 and so on. But that basic principle, that the fact that nothing can rotate faster than light, will always be imprinted in this expansion.
So the leading term will always have.
The leading term?
Will always have poles, right?
Sorry,
No, I'm saying the leading term will always have this pole. That you
yes,
cannot.
yes, you mean, yes, exactly, yes.
Only the defect part will not have these poles.
In S2 times
In
S1.
some cases, yeah,
And if you go S3 times S1, then even the defect action can have thing, but then basically you can have a term which goes like 1 over 1 plus omega 1 square, but not with the omega 2 pole,
Okay, yeah.
depending on like how you are turning on the Cartan direction.
S3 you can have without fixed points, but you're saying supposing you were to quotient with fixed points.
Yes, so in S3 what happens, there are 2 Cartan directions. If you have like the same thing, then it's like if you have 2 different directions, then and if you have same thing, then so you can create a scenario where there is a fixed locus, like by like tuning the ratio, this P1 over Q1 and P2 over Q2. And also one more point, if you have multiple ratios, this P1, so I was always writing Q beta, but if you have multiple ratios like P1 over Q1, P2 over Q2, then you have to take the LCM of Q1 and Q2, and that will be your effective Q. And then on each locus, you have to figure out that, so on fixed locus, it will be fixed by the one of the rotation, not fixed by the other rotation, and you have to write down the effective action for each one of them. And also this one more thing, that for the bosonic theories, this P over Q is a periodic, has a periodicity of 1, which basically means if you set P over Q to half, this term should not appear. And indeed that's what happens in the free boson. Like if you compute in a free scalar field theory, this term, you will see that this term drops out. So that's a check. Okay. So now I want to mention 2 more things. One is about fermions and one is about holographic theories. So for the fermions, the deal is that there is a -1 to the power f, which is and this -1 to the power of f is basically on the space, it's just a twice pi rotation. It's only act on the fermions. So we do not have any prediction of the trace e power minus beta h -1 to the power f. So we will interpret that as a new data. So for the fermionic theories, let me erase this part. So for the fermionic theories, the prescription is that, so the initial data would be this and this. And once I know this to expansion, I can predict any kind of expansion with or without -1 to the power f. And when I will be doing this stacking, I have to keep track of the fact how many times I am stacking on top of each other. Because suppose I start with without -1 to the power f, the fermions has an antiperiodic boundary condition. But then if I stack on top of each other, this thing will have a periodic boundary condition. So that means if I start with some q even without -1 to the power f, I have to relate it with something which has a periodic boundary condition. So that means I have to insert a -1 to the power f. So the upshot is that there is a -1 to the power f and you have to keep track of that in this stacking procedure. So that's one way of thinking it. And another simple way of thinking it is that you do not think of like you interpret trace as a periodic boundary condition, and think of this insertion as an insertion in the spin group. So now P over Q goes from 0 to 2. So, and then the equation as it is written holds true. So either you have to treat it as a spin group element, or you have to keep track of the -1 to the power f separately, and you have to, like, when you stack them, you have to see how many times you are stacking. So for the fermions, the punchline is, like, once you know this and you keep track of the -1 to the power f, you have this expression for. And then I have to say something about the holographic case. So of course there is a, like, in this. Sorry.
Is this true in 2 dimensions? Also,
Yeah,
these are 2 independent data.
Yeah, in 2 dimensions something more happens, because that
You have F left.
yeah,
and F
you
right
have this ns and nsr, and then, well, in 2 dimension in some sense you also have this Ramond ground state energy,
You
which is in
have
some sense a different data. But in, well, yeah, in 2D you have that, but in higher D, basically, like in SD-1 you do not, like, there is a unique spin structure, you only have this S1, and then there is only 2 possibilities, whereas in 2D you have like 4 possibilities. Okay, good. And for the holographic case, oh, and also one more thing, that if you consider supersymmetric theories, then these are indexed and they might be determined by some other things. So, like, here I am just saying in a fermionic theory, in a generic case, they are independent data. Okay. Now, so now comes.
Formula will still work.
Yes, the formula will.
Whether it's supersymmetric or not.
Yes, exactly. The well, in the supersymmetric case, yes, there can be cancellations, and
so some of the coefficients will be 0.
Yes, exactly. So that might happen. Some yes,
Okay.
exactly. Yeah. Okay. Oh, okay. Before going to holographic theory, I said I should say one more thing. So this trick of this stacking, they do not really depend on the fact you are doing you are working on a conformal field theory, because that just depends on the fact that you are doing a path integral and you can stack them on top, you can cut them and you can stack them on top of each other. So if you think of a thermodynamic limit of a massive QFT where the length goes to infinity, then this equation is true as it is written with L going to infinity limit, or the radius of the sphere going to infinity limit, even for a massive QFT. And you can check this for, again, the testing bed is a free scalar field theory. You start with the free scalar field theory, you compute this quantity, and you can see that these 2 matches in the L going to infinity limit explicitly. The only place where you use the CFT, like when you want to expand these both sides in some EFT expansion. But that trick as it is written is true for QFTs also. Okay, now the last bit, the holographic part. So for the holographic part, like, the idea is that I already told you that this kind of quantity is same as evaluating this S1 q beta times SD-1 slashed out by ZQ, where there is this action. So what you do, you basically forget about this part for a second. In the beta going to 0 limit, you can, like, extend this manifold in the bulk ADS, so this will be a black hole solution, ADS car or BTZ or so on, with appropriate temperature q beta. And then on the boundary, there is a ZQ action. You just extend this ZQ action in the radial direction. If there is no fixed point of this thing, then the solution you will get in the bulk is a smooth solution. They solve the Einstein equation, and almost by construction, they gives you the answer you want. So for example, in the ADS3 case, it will be some BTZ slashed out by ZQ, and for example, if it is Z2, then it is related to the CRT twisted black hole that Harlow and company wrote down recently. And you can also think of them as a SL2Z image of the BTG black hole, some particular transformation. There is one subtlety that appears if you have a defect, because if you have a defect, then there are all this extra data, and on this side, and on the bulk, it basically means that at the tip of the cigar, there will be an orbifold singularity, because at the tip of the cigar, the time cycle completely shrinks, and then you have this another direction phi, which gets rotated by the ZQ. But if there is a fixed point, then that will create a singularity at the orbifold point. So that will happen in ADS car if you do this quotienting. And then, like, except at the that at the singularity everywhere else it solves the Einstein equation. It gives you the answer you want up to this point, like all these contributions are noted, but that solution, the quotiented solution cannot capture this S defect. And then the prediction is that there will be some new solution which would resolve the orbifold singularity by some means. And once it gets resolved, by that resolution, it will also produce the data for this S defect. But at this point, we do not have any concrete prediction for this part from the holography side. So,
but if the bulk theory is a string theory, then the orbifold may be a allowed singularity, right?
Because of other fields and so on.
I mean, in string theory, orbifolds are perfectly regular.
Oh,
At least some
I see.
orbifolds are perfectly regular, right?
Yeah, that's true. But then, so I guess you were saying that just embed the ADS thing in the string theory, right?
Yeah.
And then it will give you a resolution, and it will also produce this data.
Yeah, presumably.
Yeah, presumably it should happen, but we do not have any like concrete computation. Yeah,
I see.
but presumably our EFT basically predicts something like that should happen, because otherwise you cannot produce this S defect data, and the solution is also singular.
Okay.
Yeah.
You can continue it into C2 mod ZQ there and then resolve it using.
Yeah, the point is near the, like very near the orbifold singularity point, it's like a flat, but then at the end you have to glue it back to the ADS.
No,
So
but to
this,
get just the defect contribution, right? You can probably do it on the C2 mod ZQ resolved.
yeah, so you can do it for C2 mod ZQ, but then my confusion is that, our confusion was that, like we do not know how to like glue this C2 mod ZQ solution, which is flat, to the ADS solution, because you cannot spoil the ADS, like asymptotically it is ADS. And like the point is, if you spoil the bulk solution too much, then you will spoil the leading answer.
Right. But perhaps the two contributions factorize in some sense so that you don't need the
Oh, I see.
extension back.
Probably,
to
but
That's what I
yeah,
was imagining.
something like that could happen. But yeah, I guess to be honest, we do not have any. We have this prediction, but we do not have a concrete resolution. And I didn't really talk about non-perturbative corrections, but you can also talk about non-perturbative corrections. Conceptually, the idea is following, that the volume goes to infinity. You can treat this beta going to zero limit as volume goes to infinity. So the SD minus 1 becomes like RD minus 1, and there is an emergent Poincare group, and there is a massive representation because you assume that there is a gap theory. And then you can think of, there are some massive particle, and there is a worldline moving on SD minus 1, and you do the worldline action of this massive particle, and that gives you some systematic corrections of which are all suppressed by e to the power minus m over beta. And so you can do this at this level, and you can also play the same, and this stacking procedure is also applicable on the non-perturbative terms, because again, the stacking doesn't really care about whether you are looking at perturbative pieces or non-perturbative pieces. So the non-perturbative piece will also get affected by those things. And so these are more or less what I wanted to say. So the punchline that I want you to remember from the talk is the following thing, that in 2D, the modular invariance gives you all these subleading informations about density of states and how the rho even and the rho odd are distributed. And in higher dimension, we do not have modular transformation, but the thing is that if you tell me this trace e power minus beta h and trace e power minus beta h minus 1 to the power f, so basically if you tell me the leading information, then I can immediately tell you the subleading information. They are all controlled by this path integral manipulation, and that's a universal. So in some sense, this EFT and this path integral trick like does a proxy for the modular invariance. Thank you.
Let's thank Sridip for a nice talk.
I have a question about your starting point, in the sense that we are interested, let's say, in high temperature expansion, in which the original degrees of freedom are very fast moving, actually,
Yes.
fluctuating. So just want to understand that you have put such a theory in some background of a metric and some gauge field because of this twisting, and you want to integrate out everything. How do you know that you get this type of a, you wrote down basically what we usually write down is a low energy effective action. I mean, you wrote R plus F square plus etc. No higher derivative terms. Can you explain that to me? How to organize the high
How do I see there is an
expansion?
organization like this?
Yes.
Oh,
That's what I want to know.
Oh, the organization is really comes from the fact that in the beta going to zero limit, the S1 cycle shrinks.
Yes.
So effectively, you want to write down everything in terms of SD minus 1.
Yes, I understand that also. If some effective theory, but how is it organized this way? Actually?
Oh, yeah, that like the proper way to, okay, I deleted that part. So you remember I wrote down this S thermal would be action of G hat and AI. So this G hat as a factor of beta inside it, sitting inside. So now once you write down the various terms, like constant P is the Ricci scalar, they are all down by some derivatives. And so those derivatives carries the expansion of beta. So in some way you can also think of this as a derivative expansion. And that's picture I guess more clear in the like hydrodynamics picture, like Loga, Siraj and all these people.
Okay, okay. I understand now. Okay, fine. Thanks.
This is the non-perturbative, I mean, certain models there are e to the power of minus
Yeah.
potential. So you miss those corrections in this one.
Oh, no, I was mentioning about that, this worldline thing.
Oh, I didn't hear it. Sorry. Yeah.
Sorry, let me explain again. So the point is that these non-perturbative terms are following. So you think of beta going to zero limit is same as also large volume limit. SD minus 1 becomes very big. So it becomes RD minus 1. And there is an emergent Poincaré group. And there is a representation of Poincaré group. So there are masses. So the point is that I assume that this theory is gapped. So basically the first mass is non-zero. So from the effective field theory point of view, we can interpret the non-perturbative terms as some particle of mass m, and then there is moving on SD minus 1. You can evaluate the worldline action of this thing, and that precisely goes like e power minus m over beta and some piece. So that's how you can characterize at least, well, the point is that I do not know how much well-controlled approximation this is because the worldline can intersect and a lot of things can happen, but at some level of single particle sector, these are the corrections. And those corrections also satisfy this stacking rule because the stacking rule doesn't really care about whether you are looking at perturbative terms or non-perturbative. So if you insert this e power twice pi I p over qj, those non-perturbative terms will also follow this rule.
I guess what I was asking earlier, yeah, indeed, I think there should be two independent data because there are the orbits of the spin structure under the modular transformations. Will be there are two independent orbits. But that raises this thing that if you were to put it on a higher dimensional torus, there would be again the modular invariance of that SLDZ will have many orbits, and so won't you have more data?
Yes, you have to specify more data. Yes, exactly. Yes, that's a good point. Yes, exactly. So then it's not just minus 1 to the power f. So basically you have to specify all possible spin structures. And then SLD, well, not all possible because some of them would be related.
Related by modular
but story would be more complicated.
There'll be an orbits, there'll be
Well, I do not say, it's probably, I should not say complicated. I mean, in some sense it will be SLDZ is there,
SLDZ and then you...
Exactly.
Just to be sure, this high energy data you'll only be using once you want to invert these formulas to get the row, or what?
Yeah, well, if you, yes, I see. The point is if you interpret energy, which probably you should, in the microcanonical ensemble, then you should do the inverse Laplace. But I guess the thing is that this thing, when you do the inverse, like this is basically integral of density of states, which is a positive measure. So you have this whole formalism and Tauberian theorems and so on, which I talked about previously. So, and you can do things and you can make sense of this integral over rho delta, but the point is this thing from here to here, like you can do things, like you can do the inverse Laplace, and presumably it would be true for chaotic theories, like where the spectrum is very dense but then you cannot prove a theorem. So, and mathematicians might scream at you. So that's why I didn't want to, I want to phrase things in a very clean way. Because the main point is that, the main point can be phrased in a canonical ensemble. So.
If not, then let's thank Sridip once again.
Thank you. But I don't know how to.
As usual,
Thank you. Yeah, I don't know how to close this thing.